You mean you have to turn it on? Oh. Works better with it on? Oh. There's actually a thing I give to my freshmen. It's squawks in the U.S. Air Force. You know, these are actually real squawks for the pilots. And one of them is right engine missing, and the mechanic's response was, right engine found under wing after brief search. You know, or one of them is IFF inoperative, and the mechanic's response was IFF usually inoperative and off mode. So, what was the one? I'll have to get a copy of it and hand that out too. Anyway, so I'll pass this around, but this is Teflon coated, and basically it's just a stainless steel wire back here, and you can imagine shoving that up through an artery in your leg up to your heart. But it has to be nice and flexible at the tip. So it's nice and flexible, and the way they make it nice and flexible is they grind the wire down to a smaller diameter, and then they wrap it with another helical fine wire, and there's a little weld tip on the very tip, which you can't really see because of the stuff, but you can feel how very flexible that is up there and not quite so flexible down there. So this is what they call the guide wire, and it's the one they run in first, and that becomes the clothesline that you kind of run everything in on. So if they're going to do a balloon angioplasty, which is basically they put a little balloon up in there that's deflated, and they get it up in there, and you got hardening of the arteries, and they expand the balloon to open up the artery, and then they go up there with the stent, which is basically a little collapsed spring, and they use a balloon to expand the stent, and they leave that in there. You know, actually I think it was in the paper yesterday that Boston Scientific had 3 recalls on their stents, and so the surgeons were getting, losing faith in them. Had an article that they were up to $8.3 million a day in sales of stents. So the doctors are back, okay? But that's just one firm. J&J's got the Cordis division that makes these things, and there's 2 or 3 others, but each one of these companies are all in the $3 to $4 billion a year worth of sales. So you're talking a $15 billion business just to sell the equipment because, for this. And then if you start adding the medical costs, you're probably talking $100 billion. And it turns out, now it's good to be a radiologist now, if you're an MD, because it turns out the radiologists are the ones who do all that. It used to be you had, heart surgeons doing heart surgery, but now it's radiologists. And the reason it's radiologists, the only way you can tell where you are is you basically do these flash X-rays on the patient the whole time he's doing the operation. Okay, and they also have to add some things sometimes to those things. They put a little platinum on there. They might plate it with platinum because platinum's nice and dense to the X-rays. Shows up better in the X-rays and stuff. So anyway, a lot of technology goes into that, but it's a big business. Okay, let me bore you with this. We have this boundary layer that we've talked about that insulates things, but it turns out that in the welding arcs, where we kind of punch through the boundary layer, we have this cold region right near the electrodes, and it turns out, and I'm pretty sure you got this paper in your notes, but you have a number of different processes that can go on. Right in the main part of the body of the plasma, it's about 10,000 degrees Kelvin, but right up near the electrodes, it's only about 3,000 degrees Kelvin. Now that's still pretty hot, and plenty hot enough to melt metals, but it turns out in terms of plasmas, it gives you at those temperatures, the plasma doesn't want to be a plasma, it wants to go back to being a neutral gas. And it turns out the distance over which electrons and ions in a 1 atmosphere arc will combine to form a neutral atom is something on the order of a half a millimeter, which is 20 thousandths of an inch. And so it turns out that's one boundary layer. The energy exchange mean free path, how many collisions does it take and how far does the electron and the ion go before they thermalize, it's about 2/10 of a millimeter, so far as that goes. And that means that you don't get into this 2-temperature fluid plasma until you get to a mean-free path greater than that. But basically, the thermal boundary layer is about 2/10 of a millimeter. So this is the electrical boundary layer, is about 1/2 a millimeter. The thermal boundary layer is about 2/10 of a millimeter. The mean-free path for elastic collisions is about a micron. And it turns out what a lot of the literature talks about is what they call the Debye screening length. How far apart are the molecules or the ions so that they can no longer see each other electrostatically. And that's about 1/100th of a micron at 1 atmosphere. And it's a complex formula and stuff. But a lot of the literature on welding will quote the Debye screening length as if it's the thermal boundary layer or this electrical boundary layer, if you will. And they're only off by about a factor of 100, or 10 to the 4th in some cases. Okay, so there's a little confusion on that. It turns out plasma physics gets to be pretty complex. And now to give you another way that it's complex, if we actually start looking at heat flow to the anode, there's gas tungsten arc welding is basically if I use a tungsten electrode. Here's a tungsten electrode, and typically I will shield this with a gas, and there will be a little nozzle that I put the gas through. So I'll have something that holds this tungsten electrode, and I'll put the electrode sticking out through the bottom of the nozzle, and I'll have this little shroud of gas, usually argon, sometimes helium, if I need the extra heat transfer and I can afford it here in the United States. But so I put this electrode in here, and there's, a big copper clamp up here, and I got hoses coming into this and everything. But this is my welding torch, or this is just one end of my welding torch. It turns out that this is a non-gas tungsten arc welding with a tungsten electrode, is a non-consumable electrode process. You're not supposed to melt the electrode. This one actually did melt, and I got another one in here. This one hasn't melted. This is a little bit bigger one. This is a 1/4 inch. This is 1/8 of an inch. And they come in all kinds of sizes. That's a 1/16 of an inch, so far as that goes. So we can pass those around. And it depends on what current you're going to carry. This little 1/16 of an inch, you can probably weld under 100 amps. And this 1/8 of an inch, you can probably go up to a couple hundred amps. And this 1/4 inch is the biggest size they typically sell. You can probably go up to 500 amps or so. You typically grind it with to a cone, and usually they put a flat on the end. And it turns out there's a lot of theories about how you need to grind this. One of them is you can't grind it with circular grinding marks. It has to be linear grinding marks and things like that. And that's just because the angle that you grind it to, the sharpness of it, and the angle of the finish, surface finish and everything, all those can actually affect how well the arc behaves. And, well, enough said about that. So if I have a tungsten electrode, W is tungsten, that's the German name, Wolfram, or actually it may be the Latin name for, I don't remember. Anyway, it's Wolfram, W for tungsten. And if you make it negative, we call this in gas tungsten arc welding, DC electrode negative is the proper type of terminology, but a lot of people in the trade will call this straight polarity. Okay? Why is it straight polarity? I don't know why it's straight polarity. But that's just the thing that people use. And it turns out you have the anode down here that you're trying to heat and melt. It will be positive. It turns out everything we've said was that 80 to 90% of the heat is carried by the electrons to the anode. But if you think about it, the cathode, where the electrons are coming out of, a large fraction of this heat down in the anode is the heat of condensation as the electrons become bound in the metal. That was the work function potential that we talked about, dropping down to the Fermi energy yesterday. Well, that means that if I'm boiling the electrons out of the cathode, they actually are taking a heat of vaporization with them. So they actually will cool the tip of the electrode at the cathode. And in fact, Professor Savage at RPI, who's passed away now, once put a pyrometer on here and actually measured the, you can't see it, let me see if we go down in this thing, measured the temperature and found you had a hot spot just up here because basically the electrons evaporating out of the you can think of them as evaporating out, are carrying the heat of evaporation with them and cooling the tip of the electrode. As a result, about 1/3 of your heat goes to the, in the arc, the power in the arc goes to the electrode, and about 2/3 goes to the anode, which is where you want it in this particular type of welding process. You're trying to generate your heat down here. It turns out this process can be run either way, but it turns out those tungsten electrodes that we just passed around, if I run this in DC electrode negative, this might take 200 amps before I would melt the tip. If I run it in electrode positive, I can run that way, but it may only take 100 amps before I melt the tip, because I'm getting 2/3 of the heat down here and 1/3 of the heat up here. The amount of current I can carry depends on the polarity of my tip. Okay, and so that's one thing to know. Another thing is these things actually had a little red paint on the back end of them, and that tells me it's a 2% thoriated tungsten. This is not just like the tungsten filament in your incandescent light bulbs. This actually has a little bit of thoria, and if you look at the package, you'll have a little radioactive symbol because thoria has slight radioactivity, just natural thoria, very low, don't worry about it, less than living in Denver, okay? You know the story about living in Denver, right? People in Denver get 4 times the radiation of people living at sea level because there's less air to protect you from the natural radiation, cosmic radiation. So it turns out taking a flight all the way across the country is equivalent to getting a chest x-ray. Okay, you're at a higher level, more cosmic radiation for a few hours. So all these people who are worried about, you know, what's going to happen, or you go through the security at the airport, and what if you got your hand in the machine? These people who are worried about things like that, or getting a dental x-ray or something like that. That is so small nowadays compared to what it used to be. I mean, they've gotten the sensitivity of the detectors down so they can see things at very, very low levels of radiation. And in fact, people in Denver, just living in Denver, you get 4 times the radiation from cosmic background radiation. And I mean, now people are going to pass a law to outlaw cosmic background radiation, right? Or we're going to have shields, or don't ask me. Anyway, it's sort of interesting how people get worried about radiation. In fact, I actually remember it just barely from being a little kid, but up through about the mid-1950s, if you went to buy shoes for your children at the store, they basically had a little x-ray machine, and you put your feet in there, and they would, with the shoe on, and they would x-ray to see how the fit was. Those particular machines would probably give you about 10 times the radiation of living in Denver, and they finally decided this was not a good thing to do. But that was kind of in the 50s. If you go back to the 1920s and 30s, when remember they discovered radiation. Marie Curie, it was Becquerel, wasn't it? Anyway, but Marie Curie won the Nobel Prize for the work she did on radiation. That was her first Nobel Prize. She actually won too. Anyway, back in so that was in like 1900 to 1910, people were learning about x-rays and radiation and stuff. In the 1920s, people used to actually drink radium because they thought it made you feel better. And well, I don't know, I never had a glass of it, so I can't tell you. But it turns out most people kind of quit because initially apparently it did give you kind of a little pickup and you'd feel better. But then over time you start to feel worse, and mostly because it was decalcifying the bones, because radium has a higher affinity for the apatite, and I mean your bones are hydroxyapatite or calcium apatite. Anyway, the radium would replace the calcium in your bones, and basically your skeleton. If you drank this enough, your skeleton would be just kind of decomposed inside your body. and you'd be getting radiation and stuff. Now, fortunately, most people couldn't afford it. This was only the rich that could do it. But there's a story, there was one guy who just thought this was wonderful, and he kept drinking it. He was rich enough to do it, and he kept on drinking it, and he figured there was something else wrong with him, and so he wouldn't quit drinking it. He figured this was the thing that was going to save him from whatever the other stuff was. He finally drank. You know, he killed himself by poisoning himself by drinking a glass of radium every day. But people used to drink other things. Since you like the stories, why is Coca-Cola called Coca-Cola? It had cocaine in it. Coca came from the cocoa bean. It had cocaine in it, and the cola is actually from caffeine. It still has caffeine. In fact, Coke has 0.36 milligrams per gram, or per, I don't know if it's milligrams per liter, whatever the units are, and Pepsi only has 0.27 caffeine. So if you're trying to get your caffeine, drink Coke rather than Pepsi. If you don't need caffeine, then drink Pepsi. You won't. Jolt actually is less than either one of them. Wait a second. No, I'm sorry. Jolt is more than Coke. It's like twice Coke or something, but it's less than an equivalent amount of coffee. Okay, coffee is a lot stronger. This is the caffeinated brand of coffee, right? I mean, you get decaf coffee, but you know how they decaffeinate the coffee? They soak it in some fluorinated hydrocarbon, which is basically a carcinogen, and it dissolves out the caffeine. So, I mean, they don't tell you these things, okay? But I can't remember. I don't remember if it's methylene chloride or something, but it's a chlorinated hydrocarbon, which are generally banned from the environment because they, are carcinogens. But in order to get the caffeine out of the coffee beans, they basically soak them in this to dissolve the caffeine out, and then they grind the coffee. So, but I mean, I guess the people who are health nuts and environmentalists don't want to advertise these things because they like their cup of coffee, They don't want someone else to be responsible for, degreasing some parts in some chlorinated hydrocarbon, but they're going to drink their coffee, and there's probably more chlorinated hydrocarbons now being used to decaffeinate their coffee than there is, anyway. It's an interesting system in the world, isn't it? But what was I going to, why is 7-Up called 7-Up? Here we go. Because it was lithiated originally until like 1931. Lithium gave you the same, is a antidepressant, okay? And they actually give lithium carbonate to people as a prescription because it can screw up your potassium, sodium, electrolyte balance in your body. But lithium is, just above sodium in the periodic table. And so lithium carbonate actually works as an antidepressant, but it's very hard to control the level of it. But 7-Up is called 7-Up because lithium has an atomic weight of 7. And when it originally came out, it was a lithiated soft drink. It was basically an antidepressant. Okay? And then in the 1930s, they decided maybe they shouldn't be selling it that way. And so they quit selling it that way. Anyway, see? And we got caffeine and Coke. And actually, if you really want to get your caffeine, you drink tea, right? Because that's where you can get your tannic acid, too. And there are a lot of people trying to shut down leather refinery, leather places all around the world because the tannic acid and the stuff that comes out from tanning leather is just really, really bad stuff. And those people really do have serious health problems. However, when you drink tea, you're getting more of it. And so, anyway. Okay. What can you say, eh? Huh? So the anode is heated by electron condensation, and so it turns out in gas metal arc welding, where I don't have a tungsten electrode, but I have a metal electrode. It could be a steel wire, it could be aluminum wire, it could be a nickel wire, it can be a copper wire, although it's a little bit harder to do copper. We call it DC electrode positive because this is the anode now, and we call this reverse rather than straight polarity. Now, why do we want this to be positive? Well, the easiest way to think of it is, what am I trying to melt here? I have some groove, some bevel groove in my plate that I want to fill up down here, and the thing that I really want to melt off is the electrode to fill it up. In gas tungsten arc welding, I'm not trying to melt my electrode, so I'm going to have the cooler one be the one that doesn't melt, and I'm going to have the base plate be the one that does melt. In this case, I actually am trying to melt off electrode to fill up some groove, some V groove or root gap or something down there. And so I'm going to switch my polarity. That's the simple way to think of it. Turns out that's not necessarily completely correct. Turns out this polarity, for reasons we might talk about here in a little bit, gives me more stable metal transfer. Drill drops have to transfer across here down to here. And it turns out this polarity gives me a more stable arc. Okay. Up here, with this polarity, with the electrons coming out of here, it turns out I can get a more stable arc if I add this thoria. I got off on this little radiation, and I forgot to tell you why we were talking about radiation. The thoria has a little bit of radiation, but it's thoria. It's thorium oxide. 2%, you can buy 1% or 2% thorium oxide powders, and basically it helps with electron emission. The electrons are coming out of the cathode. The tungsten electrode is the cathode, and it turns out the voltage, or the cathode voltage drop in tungsten is going to be 4 or 5 volts. If I put 2% thoria in there, those little spots in the thoria, or of thoria in there, will be where the electrons will come out, and there'll be about only a 2-volt drop. And so I actually generate less heat if I have a thoriated electrode. And so if you can buy pure tungsten electrodes, but you're probably going to use 20% less current before you melt it. The thoria helps cool it because, again, it's easier electron emission. And in fact, we talked about the cadmium in the light switches. It's cadmium oxide in the light switches for the electrical contacts, and the cadmium oxide does something in the same way. We don't exactly understand it fully scientifically, but basically the cadmium oxide helps cool the arc and quench the arc, probably related somehow to electron emission in a similar way to the thorium oxide in here. Now, in the United States, we still use thorium oxide because that's what they've been using for 60 or 70 years. But the Japanese did a lot of studies in the 1980s on lanthanum oxide and what were the others? Cerium oxide, and there's another one. Oh, yttrium oxide. So these are very high melting oxides. It turns out some of them are better for arc starting, for initiating the arc. They basically give you easier arc starting. And others are better at cooling the arc and keeping it, giving you better electrode life, okay? And in fact, now you can buy electrodes, and they're starting to sell a little bit better in the United States in the last 5 or 10 years, that are both seriated and lanthanated, or seriated and yttriated. And then they don't have the radioactive symbol on the package, so people don't get worried about the radioactivity. But in fact, they have longer electrode life and they're easier to start. So the Japanese did most of that work, but mostly sold by the Japanese and some Europeans. The American welding companies have only recently realized that there's some technology out there that they don't own, which is actually sort of another interesting story. Since this will go on the web, right? There is a definite not invented here syndrome in the American welding community. Since you guys are in the Navy, you might as well learn this. Lincoln Electric Company is the world's largest welding electrode manufacturer. And they, they used to call him Old Man Lincoln, but James Lincoln Sr., who founded the company back in the teens or the 20s, was, you call him conservative, or maybe ultra-conservative. For example, after World War II, he sold Lincoln Electric UK because he didn't trust the British. He didn't think they were close enough allies. After World War II, he also had sort of the same type of mindset as Henry Ford, in that Henry Ford built the River Rouge plant, where you basically brought in iron ore, and the other end of the plant you brought out cars. Okay, he had his own steel mill, and made his own steel, and did everything. Well, Lincoln Electric had that same mentality until about the 1980s, and economic forces kind of forced them to change. But I remember going through the Lincoln Electric plant about 1980 or so, or early 80s, and they had raw steel coming in, steel bar and stuff, and they had electrode power supply and copper, copper rod and stuff coming in, and they had electrode power supplies or welding power supplies going out the other end of the plant. They bought raw materials and they produced everything themselves, their own switches and everything else, because they didn't trust suppliers. Okay, they wanted to do everything themselves, and they had this same type of attitude in technology. They figured they were the biggest in the world and no one knew what they knew. And in fact, they still have that attitude. That still persists. I had to give a lecture once to Lincoln Electric. I guess they had to go all the way to the CEO to get permission to have me come give my gas metal arc lectures to 40 of their engineers. And it was a big political thing. And finally, the CEO said fine. But the director of research told all of his engineers to not ask me any questions, because if they asked me any questions during my day-and-a-half lecture, I would learn things from them. I would learn more from them from their questions than they would learn from me. So I'm given the first morning part of the talk in the morning, and I'm kind of trying to interact with them, and I ask questions and no one will respond. And at the break, it turns out one of my first doctoral student actually was working for him, and he happened to be Chinese. And I said, what's going on here? Why don't they answer questions? She said, oh, John Gonzalez told them not to. They're under orders not to. So when we come back from the 10:30 break, I start saying, I point to someone, and say, what's your name? He tells me his name. And then I ask him the question, well, how can he not respond, right? And turns out, so I was forcing them in the second half of the morning to ask questions. And after lunch, I finally convinced them that they might learn something from me. And they actually started asking questions, and Gonzalez was sitting back in the room stewing, okay, because people weren't paying attention to him. But anyway, it's an interesting culture at Lincoln Electric, which has helped stifle innovation in the United States welding community for at least 50, if not 80 years. I mean, at one time they were the leader, but they still think they are. But the world is passing them by. Okay, so I had this tungsten electrode. And I talked before about a plasma arc. This is would be the equivalent of if we were talking flames, this would be burning at 1 atmosphere pressure. There's no surroundings or anything. And that would be the equivalent of a pre-mixed flame, if you will. You're just heating things by electrons or the electric current going through here, as opposed to a chemical reaction between gases. But remember, there was a jet burner where you basically combusted the gases in a chamber, and I mentioned this once before. Basically, plasma arc welding is, we talked about this in plasma arc cutting very briefly. You basically strike your arc inside a chamber and let it come shooting out as a very high velocity flame. So this actually happens to be the tip of a plasma arc cutting machine. And if you look inside, this is the copper, and you'd have a tungsten electrode that would fit right inside here. And this is your chamber where you're going to generate your arc. The arc is actually going to be struck from the tungsten electrode up towards this. And then I told you how they had replaced the tungsten with hafnium so they could use air in here. Another thing on this is if you look carefully at this, actually there's two of them for just different shaped ceramics. If you look very carefully at the tip, you'll see the hole coming through the center, but then you'll see an annulus around the side. And if you look in here, you'll see the hole, but if you look around here, you'll see little spacers, and there actually is gas that's going to be injected in the side of these little spacers, and it's going to come around that little torus around the hole. So you're going to inject cold gas out of this hot plasma shooting out. And it also, if I remember inside here, there are some kind of turbulators to help give you a swirl flow. And so you actually help stabilize this jet shooting out by doing a cold swirl. The cold swirl quenches the plasma on the outside, helps concentrate it, because the current, remember that I told you the current is the temperature of the arc is going to generate whatever temperature is necessary to give enough ions to carry the current, okay? So you'll get a hotter arc if you an arc is kind of strange. If you cool the outside of an arc, the center of the arc gets hotter because you got to carry the same current in a smaller diameter. So I got to ionize it more. So that's what this swirl is going around here. So you actually have two gas flows. You have one gas flow coming through here and an arc struck in here, which generates the plasma, and you actually also carry current out through here to the base plate in one type of plasma cutting, or plasma welding. And so there are two types, it turns out, plasma either cutting, well, plasma cutting is really just one, but plasma welding you can have transferred arc or non-transferred arc. Transferred arc is I've got my tungsten electrode, let's just call it a tungsten electrode because I'm going to be welding here rather than cutting, and I got my copper piece here, and I'm going to generate an arc in here, sometimes called a pilot arc, and it will give a little flame. If I just holding the torch, I can hit the trigger and I'll see a little flame shoot out into the middle of the air, plasma flame shoot out about a quarter of an inch into the air. Here's my workpiece down here. In transferred arc, and I also will have another thing out here, this other little annulus that I'll get this little swirl flow going around here to help cool the outside of the arc and stabilize it. I will now actually have a more complex circuit and run some current all the way down here. And why do I want to do that? Because 90% of the heat is carried by the electrons. Remember? This is transferred arc, and by transferred it means there is some current going across the gap into the workpiece. Non-transferred arc is essentially the same thing. Let me just do it like this. But the arc is only up here, and I just have a plasma gas. There is no connection to the workpiece, electrical connection to the workpiece. So in fact, with this non-transferred plasma arc, I just have a plasma flame at 10 to 15,000 Kelvin heating a surface. I can heat a ceramic if I want. It doesn't have to conduct electricity. Over here, I can heat metal. I have to have something that's conducting. But the difference is, here I can get up to 20,000 watts per square centimeter, about double the what I can get out of a simple gas tungsten arc, which is about 10,000 watts per square centimeter. Why? Because I got a higher velocity, my boundary layer is thinner, I get more conduction across the boundary layer. There's no more heat carried by the electrons, it's still the same 80 or 90%, but instead of only 10 or 20% carried across the boundary layer, with a thicker boundary layer, I can get substantially more heat because of a much higher velocity coming out of there. So it turns out I like plasma arc for welding aluminum. I like plasma arc for welding copper. They have very high thermal conductivities. I can get much more efficient welding. The space shuttle main tank is welded by a special type of plasma arc. Okay? NASA can afford anything. Well, anyway, and they weld the space shuttle main tank, which is aluminum, of course, by a what they call variable polarity plasma arc. In non-transferred arc, you only get about 2,000 watts per square centimeter. And the reason is you don't carry any current. No electrons. Now this one actually is a little bit higher in terms of watts per square centimeter because I had the swirl that constricted this arc. This is not as broad an arc. The plasma arc is not as broad an arc as the gas tungsten arc, which is just free to the atmosphere. The gas tungsten arc kind of spreads out and forms a bell shape. In fact, where does the bell shape come from? The bell shape actually comes, well, I got another, we'll talk about the bell shape in a little bit. So there's a big difference, and again, the difference between transferred arc and non-transferred arc, both of which are used. This one used primarily when we don't want very much heat, or we're trying to heat something that's non-conductive, non-electrically conductive. This is always used for cutting. You need that type of heat intensity to do the rapid melting that you need for cutting. So you're always going to have a transferred arc for cutting. And in fact, because it's a constricted arc, you may have in here not just 30 volts, but you can have 100 volts across this thing because you've quenched that arc on the outside, made it narrower, sharper, concentrated the heat, and that's going to require a higher voltage to get the higher temperatures in the plasma to cause greater ionization in the smaller cross-section. Now, that creates all kinds of safety hazards. The nice thing about a gas tungsten arc, I don't care, it's basically idiot-proof in terms of someone trying to electrocute themselves, okay? The only way you electrocute yourself with a gas tungsten arc is if you open up the back of the power supply and stick both fingers in, okay? You can get a pretty good shock if you don't know what you're doing. You know, hold one end of the tungsten electrode and ground yourself to the base plate, you know, and you'll get 30 volts across you, which could give you a pretty good shock, but 30 volts won't kill you. Might you know, kind of ruin your day, but it won't kill you. With 100 volts, you now have the potential, if someone wants to somehow reach up in there, now they're going to have to take some piece of metal or something that's, you know, it's not, you'll see, it's not that easy for someone to get up in there and short out to this. If you actually saw the rest of the shielding around this thing, they put lots of shielding around this thing because if someone did touch the metal at the tip and was grounded, they'd have 100 volts and they'd electrocute themselves. So they're aware of this and they've tried to make it idiot-proof, but it is potentially a hazard. In fact, the open circuit voltage on the power supply can be 400 volts, whereas the open circuit voltage on the welding power supply is probably only 100 volts, and once you draw much current, it's down to 30 volts. So that's transferred, non-transferred plasma arc. Oh, let's talk about variable polarity. We talked about, okay, this gas tungsten arc, we said, well, you like to use straight polarity or DC electrode negative for a gas tungsten arc because you don't want to melt the tungsten, you want to melt the base plate. And then you use the opposite for gas metal arc where you're trying to melt the electrode and fill up some gap in between the plate. Well, it turns out when I'm welding, particularly aluminum or magnesium, and I really don't want to weld magnesium, it can be welded, but magnesium is very, very susceptible to stress corrosion cracking, and all you need is some stress on the magnesium, and it will just crack like mad. And welding in general creates residual stresses, okay, in heavy plate and heavy section. So if you go look at something, I used to have a magnesium hand truck. Actually, I guess I still have one at home. I had two at home. Someone borrowed one on the no return plan. But anyway, if you look at a magnesium hand truck, everything's bolted together, no welding. Because you don't weld magnesium unless you stress relieve it. And it costs a fortune to stress relieve it, you know, in terms of everything. So it's not worth it in most cases. But anyway, in aluminum, we do weld aluminum. And when you weld aluminum, aluminum has this very, and magnesium both have this very tenacious oxide. And it turns out that if you have a very thick oxide, and the oxide melts at a high temperature in both of these, and the metal melts at a substantially lower temperature, you have a problem if the oxide's very thick. And by very thick, it's the type of oxide that can grow thick in a month sitting around. So unless you have freshly cleaned, and I mean freshly, it's not like cleaning copper for soldering where it has to be within minutes or hours, but unless you've freshly cleaned it within the last week or two, you have a hard time welding on aluminum or magnesium, unless you switch the polarity and go to what they call reverse polarity, and now there is actually a cleaning action. And I guess I could have searched around the lab to see if I had a piece of welded aluminum that hadn't been cleaned up. But you actually can see, if you change the polarity, you can see how you break up the oxide surrounding the weld. And if you watch it through the lens while it's welding, you can see surrounding the outside of the weld as you're moving along. You can actually see the cleaning oxide, the oxide as it's being cleaned off. Now most people, if you go to the welding handbook, they'll tell you that that's because when you change the polarity, all those positive argon ions are going to be impacted against the surface here, and they're going to break up that oxide. Well, that's not true, okay? That's the theory, and that's all the theory anybody knows, but it turns out if you try to do this type, if you change the polarity and you're welding on aluminum in a very, very, very dry environment or without oxygen, you will find that it doesn't matter what your polarity is, you will not get the cleaning action. And the person who learned this, and we've never published it, was actually Lieutenant Commander Dan Reese doing his thesis on welding of titanium in 1983. Dan retired about 2 years ago as captain of Pearl Harbor shipyard, right? He retired because his father was an old welding person in the welding industry, and I knew his father as a welding engineer before I knew Dan. But anyway, Dan worked on welding of titanium. He was doing gas metal arc welding of titanium. We had a glove box where we could get down to 10 to the minus 18 atmospheres of oxygen in absolutely pure argon. It took about 2 days to do it, but you could get this ultra pure situation. And we got unstable metal transfer in gas metal arc welding. Okay, this was after the Alpha sub, remember, and the Navy was trying to figure out how to weld submarines, and we know that we weld submarines with gas metal arc when we're doing steel submarines. And so the U.S. Navy had invested all this money in trying to do gas metal arc welding of titanium down at David Taylor, and it never really worked to people's satisfaction. So we were doing some studies, and Dan was doing it. And the titanium was expensive and stuff, and so Dan would do some of the setup work with aluminum. Well, it turns out he found that ordinarily you're using this type of reverse polarity, which give you the good cleaning action on the aluminum. Except he did it in his glove box, no cleaning action, because we had no oxygen around. If he put fresh oxygen in there at only 10 to the minus 12 parts per million, but 10 to the minus 12 atmospheres of oxygen in there, which is what you got straight off the liquid argon tank, he would find the aluminum welded just fine. And so, but then if he cleaned it up, it wouldn't do the cleaning action. And it turns out that he then tried it with titanium, and we came up with a theory that we never ended up publishing, just because I got tenure, and tenure means never having to write the first draft, and he went off to the Navy, and he's never published it. But it turns out he could add water vapor or he could add oxygen to that arc, and he could get the cleaning action back. And it'd be so little water vapor or oxygen, you'd be talking in the parts per million regime. So there's something when you're adding water vapor, you're just adding oxygen. So there's something about oxygen that helps this cleaning action when you have this polarity. It's not the argon ions like the welding handbook says, so far as that goes. And let's see, where are we? So that's, and so what do we do? It turns out in gas tungsten arc welding, or what's this variable polarity that NASA uses to weld the space shuttle, the variable polarity plasma arc. It turns out, since you would like to get the good cleaning action with gas tungsten arc welding of aluminum, you'd like to run reverse polarity. But to get good efficient melting, you'd like to run straight polarity. So what do? You run AC, and you get a little bit of both. So AC welding is gas tungsten arc welding is commonly used for aluminum. However, because of this asymmetry of the electron flow between the cathode and the anode, if you just run straight AC, there is a rectifying action, and you'll get a little bit of DC offset, because the current that goes through when the aluminum is negative is not as high as the current that goes through when the aluminum is positive. So you get a slight offset rectification. It screws up your transformers. They like to have things balanced in terms of positive and negative cycles, in terms of magnetic fields and whatnot. And so what people have done is they built special types of transformers that essentially balance out that DC. So you put a different voltage on the positive pulse than you do on the negative pulse of your AC welding. They call it variable polarity plasma arc welding, and you actually get with variable polarity plasma arc, if you're willing to pay $50,000 for a power supply, you can get beautiful welds, and NASA does. Okay, when they're making space shuttle main tanks, they don't do that a whole lot anymore. Okay, the next thing we want to talk about, which we can probably do in the last couple of minutes here, is plasma jets. I've got this electrode up here, and the current's running down through here. And if I look at the Lorentz force, if I have a current going this direction and I have a self-magnetic field induced by the current, because anytime you got a current, you got a magnetic field going around it, right? According to Maxwell's equations. That will create a J cross B force. You guys remember, you guys have had some of your electrical stuff yet? Or maybe not, but anyway. It creates, that's just basically, that's what causes motors to spin, right? J cross B force. If J is axial, B is circumferential, the force is going to be radial. Remember vector cross product, 3 different perpendicular directions? It turns out that the force will be radially inward. If I take the magnitude of that, since the current, the magnetic field, the self field, is proportional to the current that I'm putting through there, and if I'm talking current density, the force is proportional to the magnitude of the current density squared. I have a higher current density up here than I do down here because I have a smaller area than I do down here. So I end up with a higher radial force up here than I do down here. This is the force, small force down here, radial inward, large force up here. What if I have a radially directed force pattern like this, you know, high up here, small down here, what's the pressure gradient in this direction? It's pressure gradient in this direction, right? High pressure here, low pressure here. I mean, if I squeeze on the sausage, you know, it's going to push the stuff out the other end, right? Well, it turns out you have what these are called plasma jets. You have electromagnetically driven flow due to the Lorentz force, and off the tip of that welding electrode, you will get jets of 500 miles an hour. And in fact, that's why I can weld overhead. Why do the drops go up when I weld overhead? You never thought about it before, did you? Some people say, well, I actually touched the little drop and surface tension carries it up. No, no, no. If you actually look at it, you got drops going up against gravity if they're small drops. Turns out if they're smaller than about 1/16 of an inch, the plasma jet is sufficient to blow them up, and then surface tension does hold them in there. Remember, if they get much, the well pool gets much bigger than a couple of 1/8 of an inch, it's going to fall back down your face because surface tension won't hold it in. Gravity becomes dominant. But it turns out the reason I can weld overhead is because of these plasma jets. Okay? And this jet coming down creates this flow, which creates the boundary layer. It turns out if I go to very high frequency arcs, and I actually can get some arcs, well, with special power supplies, up in this 100 kilohertz regime. You asked me the other day about, you know, the response time of how quick the arc could go on and off. The plasma frequency response time is on the order of 100 kilohertz. If I actually turn the arc on and off at 100 kilohertz frequency, I will not develop the plasma jet, supposedly, and I get a football-shaped arc as opposed to a bell-shaped arc. So why do I get a bell-shaped arc? I get a bell-shaped arc because I have this plasma coming down, hitting the surface and blowing off to the side. I'm really seeing the bell is not the gas flowing this way, it's coming down and going out, right? So I get a bell-shaped arc because of these plasma jets. Now the plasma jets are also responsible for such things as it depresses the well pool, okay? And there's the old joke when Michael Dukakis was running for governor before he ran for president unsuccessfully. They were talking about doing the big dig before they did the big dig at this in the 80s. They said, they called it, before they called it the big dig, they called it depressing the central artery. And the question was, how do you depress the central artery? You have Michael Dukakis talk to it for an hour. Okay, so the other joke is you had George Kavarian sit on it. George Kavarian was Speaker of the House of Representatives in Massachusetts. He weighed about 450 pounds. And you either had Michael Dukakis talk to it for an hour or you had George Kavarian sit on it. So that's just the kind of jokes in Massachusetts anyway. So anyway, we'll talk some more on Monday, about arc pressure and depressing well pools and